Welcome everybody in introduction to Apache Spark architecture. My name this is the introduction to the welcome everybody in introduction to Apache Spark architecture. My name is Emil Kamiński, and today we will talk about the things like a driver, workers. We will learn Spark UI, RDDs, transformation, and many other things. Basically, whenever you are planning to do any kind of data engineering job with Apache Spark, this is essential. But also, if you are when you are working as a data scientist or data analyst, this knowledge will come handy. It will help you to troubleshoot some things or optimize your flows. And the way things are organized today, we will spend around 50% of our time talking about the theories. I have a couple of slides prepared for us, and a second 50% of the time, we will actually open databricks and run a couple of queries, then open Spark UI and try to understand what was happening under the hood. Let's get started. First things first. If we open Apache Spark documentation, that's a definition we're going to get, and it's actually pretty important. Apache Spark is a unified computing engine and set of libraries for parallel data processing on the computer cluster. So why this is important? Well, first of all, Apache Spark was never designed as the storage system. The thing it do well is it takes the data from one place, do some magic, some transformation, and send it or save it to another place. The second thing, Spark can shine on the computer cluster, meaning whenever you have enough data that you need multiple machines to analyze it, Spark is the way to go. And the second way around, if you have a small amount of data which fits your personal computer, you have already better solutions than Apache Spark, even pandas in Python, and there is absolutely no need to learn Apache Spark. Now, talking about the libraries or module, actually the ecosystem of Spark is pretty rich. The first one and the most important is Spark SQL. This will allow us to write a SQL type queries to Apache Spark. Today we'll be doing that mainly with Python. We have also a module for stream processing, for distributed machine learning, for analyzing the graph databases. This is not really well developed module. And at the end we have something for R fans. So if you like to use the language R, you have a dedicated module in Apache Spark which will allow you to use that language. And talking about languages, Apache Spark was mainly written in Scala, but you don't need to know Scala to use Apache Spark. You can use Java, Python, SQL, or R. There are some benefits of Scala, but in 99.999% of the cases, you don't need to use it. And if you don't even know what is it, you can think about the Scala like some kind of Java. It also runs on the Java virtual machine on the JVM. And we can find Apache Spark in many different places. In Databricks, that's where the founders of Apache Spark works, but also in all main clouds, there is some kind of the flavor of Apache Spark. Let's talk about main components. I'm sure that you heard the terminology of driver and executor. So both of them are processes which run on the JVM, Java Virtual Machine, and usually driver and each executor is being run on the separated virtual machine for the sake of managing that and avoiding the conflicts. It can happen that we will have two executors on one virtual machine, but it's not common. And there is also a third very important which, but also in all main clouds, there is some kind of the flavor of Apache Spark. Let's talk about main components. I'm sure that you heard the terminology of driver and executor. So both of them are processes which run on the JVM, Java Virtual Machine, and usually driver and each executor is being run on
JRE. The JVM, JRE, and JDK. As a Java developer, you hear J acronyms pretty much all day, every day, but these are the three main ones you'll definitely be expected to know. At the end of this video, you'll know exactly what all three of them are, what they do, and how they fit together in this J-filled world of Java. My name's John, and I'm a lead Java software engineer. I also have a full Java course available, and I'll link it down in the description. There you'll find over 8 hours of is just run Java programs on your computer, and you never need to. Basically, if all you ever want to do is just run Java programs on your computer, and you never need to create or modify a Java program, you'll want to install the JRE to do that. The Java runtime environment contains everything you need to run a Java program on your computer, and that includes a couple of main things. It includes the Java standard library, which is basically just a bunch of helper classes and files that all Java programs use to do what they need to do. So that would include things like all the classes in the java.lang package, like string, math, exception, and throwable, and even the object class, which is the root of all other Java classes. It has java.util for things like lists and sets and maps, java.io for all kinds of input and output, java.sql for interacting with databases, and tons more, all built in right there as a part of the JRE. The other very important part of the JRE is another one of our J acronyms, the JVM. JVM stands for Java Virtual Machine. Java Virtual Machine is simply responsible for executing a Java program. It loads up all the bytecode from your .class files that you generated by compiling your .java files. It loads all of them up into memory and runs your program. Now, that sounds pretty simple, but what's cool about that is all the hidden stuff that it does behind the scenes to help your program run smoothly that you never even need to be aware of. So for example, Make sure that your program runs great on whatever platform it's running on, Windows, Linux, Mac OS, whatever, without you having to make any changes to your program. It handles memory and garbage collection automatically. It manages multi-threading if your program uses it. It does some built-in security checks. So all you really need to know is that the JVM is what's responsible for loading up your program into memory and executing. So the JRE includes those two things, the JVM and the Java standard library. With those two things, the JRE can run any program that you give it. The JVM will take your Java program, marry it with all the classes and things from the Java standard library that it needs in order to do its job, and then it'll run your program like a champ. However, if you want to actually be able to create Java programs, which I hope many of you.
Have you ever wondered how Java achieves its write once, run anywhere paradigm? It's all thanks to the semantics of bytecode and the power of the Java virtual machine. How does it really work behind the scenes? Let's uncover the secret that makes Java both universal and efficient. So what exactly is bytecode? Think of bytecode as a middleman. When you write Java code, you save it in a .java file. But before the computer can understand it, the Java compiler converts it into an intermediate format called bytecode stored in .class files. This bytecode is platform independent, meaning it's not tied to any specific hardware or operating system. Bytecode can be interpreted by any Java virtual machine, ensuring that your Java program runs consistently across different platforms. For example, if we compile this hello world.java file, it generates a file called hello world.class. That's the bytecode we're talking about. Now let's talk about the Java Virtual Machine, or JVM. The JVM is responsible for translating bytecode into machine code that your specific device can understand and execute. It's the translator that takes the universal bytecode and adapts it to the architecture of your operating system and hardware. It's fully multi-platform. You have Windows, Mac OS, or Linux all running the same Java app. This is how Java achieves its famed portability. No matter where you run your code, the JVM ensures it runs the same way. Let's break down how the JVM works in three main steps. JVM ensures it runs the same way. Let's break down how the JVM works in three main steps. First, the class loader loads the bytecode into the JVM. It organizes and links the code, making sure everything is in place. Before running the code, the JVM verifies the bytecode to ensure it's safe and doesn't break any rules. This prevents your system from running malicious or incorrect code. Is in place. Before running the code, the JVM verifies the bytecode to ensure it's safe and doesn't break any rules. This prevents your system from running malicious or incorrect code. Finally, the bytecode gets executed. This involves the just-in-time compiler, which translates bytecode into native machine code for faster performance. Initially, when a Java program runs, the JVM interprets the bytecode one instruction at a time. This means it reads the bytecode and translates it into machine code on the fly, which allows the program to start executing immediately. However, interpreting bytecode one instruction at a time can be slower compared to running directly in native machine code. This is where the just-in-time compiler comes in. The JIT compiler analyzes the bytecode as the program runs and identifies the section of code that are frequently executed, often called hotspots. Instead of interpreting these hot code, water the just-in-time compiler, which rules. This prevents your system from running malicious or incorrect code. Finally, the bytecode gets executed. This involves the just-in-time compiler, which translates bytecode into native machine code for faster performance. Initially, when a Java program runs, the JVM interprets the bytecode one instruction at a time. This means it reads the bytecode and translates it into machine code on the fly, which allows the program to start executing immediately. However, interpreting bytecode one instruction at a time can be slower compared to running directly in native machine code. This is where the just-in-time compiler comes in. The JIT compiler analyzes the bytecode as the program runs and identifies the section of code that are frequently executed, often called hotspots. Instead of interpreting these hotspots repeatedly, the JIT compiler compiles them into native machine code during runtime. This means that for these frequently executed parts, the JIT compiler turns the bytecode into optimized machine code, which can be directly executed by the CPU, bypassing the need for further interpretation. As a result, once the JIT has compiled these critical sections, the program runs much faster. Here's a quick example. Let's say we write this simple Java program. This program defines a class called hello world with a main method, which is the entry point for any Java app. And inside the main method, it calls system.out.println, a built-in function that prints the string hello world to the console. When compiled, the .class file contains bytecode that looks like this. This is what the JVM reads and executes. Bytecode is a platform-independent, low-level representation of Java code that can be executed on any system with a JVM. The JVM interprets or compiles this bytecode into native machine code, ensuring that Java applications run.
Great, good.
Consistently across different platforms. The JVM also handles memory management, garbage collection, and runtime optimizations like just-in-time compilation, making Java efficient. It provides a secure execution environment by enforcing access control and verifying bytecode before execution. Thanks to bytecode and the JVM, Java abstracts away platform-specific details, which ensures that applications are portable, secure, and efficient across any environment. If you learned something new today, don't forget to like, comment, and subscribe.
on the separated virtual machine for the sake of managing that and avoiding the conflicts. It can happen that we will have two executors on one virtual machine, but it's not common. And there is also a third very important element, which is called cluster manager, like Apache Yarn, Mesos, Kubernetes, or Spark standalone. And this is a component which guarantees delivery for us of executor and drivers, and we can run our application. So let's say that we have a data which we want to analyze, and we write application. We can write it in Scala, Java, Python, SQL, or R. So we write application, and application communicates with the driver through something what is called Spark session. That's the only entry point for us to Spark. Now, driver takes the application and try to figure out what we want to do with the data. Once it's figured out, and once it will figure out what's the most efficient way of doing that, executing that application, it will split it into the tasks which will distribute to the executors. And each executor can process in parallel multiple tasks, as many tasks as it has slots for the execution. And it will have as many slots for the execution as many CPU cores. So in our example, we have two executors. Both of them are having 4 CPU cores. Therefore, they are having 4 slots, and therefore they can process 4 tasks in parallel. Now, driver sent a task to the executor, and it also sent information which executor should analyze which part of the data. Then executors grab that data, exchange the information between each other if there is such a need, and send the results to the driver, or save it to the files, or send it somewhere else. Not always have to be sent back to the driver. So that's how the things looks on the very high level. So let's start looking into some examples, and after that we will jump to the databricks and see how exactly the same example works in Apache UI. So let's say that we have application which want to count the number of the records in our data set. And the data set is of course represented by a blue bars over here, and we have millions and millions of that rows. Our application communicates with the driver through a Spark session. Driver takes that application and analyze what's the optimum way of executing that, and also analyze a data.
क्या था
how much data we want to count, how many executors we have, and what is the most efficient way not only to execute an application, but also what is the most efficient way of distributing that data set to the executors. So it looks on the data and decide on how this should be split into something what is called partitions. Next, it sends the tasks to the executor to grab a different part of the data and assign it with the task to each and every slot. And in the slot 1, 2, and 3, we have a similar amount of data. In the slot number 4, we have less data. This is normal situation. Now, the first task will be to do a count locally on each slot. So executor starts to execute a task, and it will happen that in this case, slot number 4 will finish first because it has the smallest number of the data. Then slot number 1, slot number 2, and slot number 3. In this case, all the tasks were successful. It can happen that some of the tasks will fail, and the driver will need to reassign a task to another slot. But in our cases, all the tasks were successful, and we are halfway done. We have a local count, but we don't have a final number. The next task, which driver will send to the executor, it will assign one executor to get all the data from all other slots and from all other executors, like in this example. And another task it will send to this executor will to perform a final count, and that will be the final count. And then depends on the application. The instruction may be to send a data or save it to the file, and then there is no need to communicate the results to the driver. Or the instruction may be that give me the number because I want to display that to the user. And in such a case, there will be additional communication happening between the executor and drivers. And the driver, in our case, we will just display that to the user. Let's discuss the big elephant in the room. During the examples, we will be using something that is called Spark UI, and we will be using that a lot. Spark UI is a really powerful tool available by default on port 4040, which will allow us to understand many things which are happening under the hood and optimize our workloads. The thing is that it's not really modern looking, it's not really super intuitive starting from the day one. But for this or another crazy reason, once you will start using it, once you will start playing with it and try to understand what's displayed there, sooner or later, it will become your second nature. Therefore, if you will not get it at the beginning, just absolutely don't worry. Try to open it on your side and try to just follow me and you will be good. Okay, so we are now in the databricks in our first notebook where we are going to start exploring how Apache architecture really works. And first things first, we are using a small cluster with 2 workers. Each worker is having 8 gigabytes of memory and 4 cores. So in total, we have 16 gigabytes of memory and 8 cores. And if we have 8 cores, it means that we have 8 slots. And the driver is the same, 8 gigabytes and 4 cores. And at the beginning of each more acres, we are going to start exploring how Apache architecture really works. And first things first, we are using a small cluster with 2 workers. Each worker is having 8 gigabytes of memory and 4 cores. So in total, we have 16 gigabytes of memory and 8 cores. And if we have 8 cores, it means that we have 8 slots. And the driver is the same, 8 gigabytes and 4 cores. And at the beginning of each notebook, we are going to have a small setup. This is nothing what you want to have in the production, but whenever you are experimenting, you may want to have it. We are disabling caching data on the storage or on the workers nodes for the sake of consistency of each and every example which we'll be showing. We want every example to start fresh. So at the beginning, we are disabling caching. And the second thing is this is our at the beginning, we are disabling caching. And the second thing is this is our sample data for that notebook. In each notebook, we'll be using fairly similar sample data, and this is available in each Databricks instances. It's examples of the data about New York City taxis and the trips, and that's how it looks like. We're going to have multiple files and its size, and the reason I like that file, I like that data set. Well, first of all, it's available in all Databricks instances. Second thing is that those files are fairly significant in size, like in this case, we have a data from 2009-07, and it's having 465 megabytes. So it's a good data set to experiment with different performance and how different functions behave. And let's look on our first count example, so about 2009 data, and here we are using Spark to read all the CSV files from that location, which are about the year of 2009. So in total, we are reading approximately 5 gigabytes of data, and then we want Spark to count it. So let me run it. And what we are going to see is that Spark is actually starting something that is called a job. We will be talking about the jobs as well as the stages or the task later on in details, but we can see that straight away. This is the job number 0. It's the first job. The number starts from 0, and it's having one stage, also called stage 0. In that stage, we have one task to be run, and so far 0 has been completed. And once it will be completed, Spark will start a second job, also with one stage. But here we are having 12 tasks, and 8 are running in parallel because we have 8 slots. And as we can see, some task has been already completed. There can be basically 2 reasons for it. First of all, the partitions assigned to the task are smaller than for the rest of the tasks, or simply that slot is faster. So 8 tasks completed, 4 are running. And now we see that all the 12 tasks have been completed. There was one more additional job being triggered by Spark with only one task, but it was very fast. And now we can investigate further details in the Spark UI. There is multiple ways you can get into the Spark UI in the Databricks. You can go there by clicking those views, or you can go and click on your cluster, and then here you have a link to the Spark UI. We are going to have a Spark UI always open in the second tab, so we can quickly switch between it. And what we see by default is we see the number of the tabs on the top, like jobs, stages, and so on. The most interesting for us in a couple of next examples will be jobs, stages, and SQL/data frame. By default, I'm in the jobs. And in this tab, for the time being, I see 3 jobs, 2, 1, 0. And those are jobs which was visible over here, job 2, 1, and 0. And from here, we can already see some details about those jobs, meaning the duration of it. We see that the second job, the job number 1, took the most of the time. time, 1 minute, we see the number of the stages in each of that job, and we see the number of tasks in each job. This is the job which actually was the only one having more tasks than one. So it would be nice to investigate further details about that job. Usually, we will be focusing on the job which took the most of the time, and in our case, it's this one. And we can do that very easily by clicking in the description over here, and it will take us to a bit of different view where we see something what is called DAG visualizations, which again will be explained in details later on, but it already gives us some idea what was happening in that job. At the beginning, there was a scan of the CSV file, then there was some computation. Later on, it will be explained what the whole stage code again means, and then there was exchange. And whenever you're going to see exchange in the DAG visualization, it means that there was a data shuffling happening between the executors. So exchange always stands for the data shuffling. And if we scroll down, we see this stage. So we can also click on that stage and it will take us to further details. And now, as you can see, the tab on the top has been changed to stages, where we see that the total time across all tasks, it was 6.9 minutes. And the input, and which means that there was 10 already gives us some additions back to that very easily by clicking in the description over here. And it will take us to a bit of different view where we see something what is called DAG visualizations, which again will be explained in details later on, but it already gives us some idea what was happening in that job. At the beginning, there was a scan of the CSV file, then there was some computation. Later on, it will be explained what the whole stage code again means, and then there was exchange. And whenever you are going to see exchange in the DAG visualization, it means that there was a data shuffling happening between the executors. So exchange always stands for the data shuffling. And if we scroll down, we see this stage. So we can also click on that stage and it will take us to further details. And now, as you can see, the tab on the top has been changed to stages, where we see that the total time across all tasks, it was 6.9 minutes. And the input size, so how many data we have read, and we read in our small application 5.7 gigabytes of data from the storage. And here we have again the DAG visualization, not so important, but once we will scroll down, this is super important. We are going to get the visualization of our task over a time. Each of that bar represents a task. And immediately from that view, we can figure out that we have two workers and each worker is having 4 CPUs. And the way we can figure this out is, first of all, the worker are very easy to spot. We have here a worker number 0 and the IP address, and the second worker, and in each worker, if we look closer, we have maximum 4 tasks being executed in parallel. Here is very obvious, 1, 2, 3, 4, but the second worker is more interesting, 1, 2, 3, 4, but then another task are starting, but those tasks are starting only if there is previously other task finishing. So this task has started only when this task has finished. So if we take a look over here, we have 4 tasks in parallel. At any given moment of time, we are going to have 4 tasks being run in the parallel, unless we are finishing the computation, then of course there will be less tasks. So this is a very interesting view and we'll be coming here pretty frequently. And once we are going to scroll down further, we are going to see another interesting data, this time summary metrics for 12 completed tasks. Here, those data will be interpreting also frequently. If you don't follow at this stage, don't worry. In each and every example, we'll be coming here and explaining different part of everything what you see here over on the screen. And what I would like you to pay attention to is the input size record. That's basically the information about the size of the partition. And we see that the smallest partition assigned to the task, minimum, the smallest, was around 457 megabytes, and the maximum on the right, partition assigned to some task, was 540 megabytes. So just like in our example in the presentations, the partition may be different in size. And if we scroll down, then we see the aggregation metrics per executor, which is also very interesting. So we see that executor with the ID 0 has executed 4 tasks. It was also visible here. So here we have the 4 tasks. And second executor has executed 8 tasks. And the total memory read, here 2 gigabytes, here always almost 4 gigabytes. So also very interesting. And here we have the further details about each and every task, how big partition it got, or how long time it took. In our cases, all the tasks have been successful. It may be that some tasks will fail. Then the driver will assign that task and that partition to another executor. So we are going to have actually more tasks. But in our cases, everything was successful. And now let's go to another interesting tab, which is in the middle. It's called SQL/data frame, where we are going to see a bit of higher level, a bit of aggregated information of what happened. So in our cases here, we're going to have 2 entries. And on the right, you have information for which job each entry is and the duration. And we see that the job which took long time is over here in the first entry. So once I will click it, it will take us essentially to the same information, just represented a bit more differently. And this time we are reading that visualization from the bottom. So at the beginning, there was scan of the CSV files and the information about how much data we have read. Then moving up, there was a hash aggregate. And that was on our presentation the first time the count happened on each slot. So here we are doing the first count. And as the output records, we got 12 records. 12 records because we have 12 tasks, and each of that task finish its job with one record. And then the next step is exchange. And exchange, again, it's a data shuffling. It's moving data between the executors. So we see exchange happening, very small data being exchanged, of course. In this example, later on, we are going to have examples where there will be a lot of data moving. And then final count happening over here. And the results are being sent to the driver for the sake of displaying that for us. So that's the whole idea. We will be talking about that in detail shortly and explaining more things. Now, moving back to our notebook, let's run a second example where this time we are running a data for 2009 and full. There will be then the next out, and that was on our presentation. Move visualization from the bottom. As I will click it, it will take us essentially to the same information, just represented a bit more differently. And this time we are reading that visualization from the bottom. So at the beginning there was scan of the CSV files and the information about how much data we have read. Then moving up, there was a hash aggregate, and that was on our presentation the first time the count happened on each slot. So here we are doing the first count, and as the output records, we got 12 records. 12 records because we have 12 tasks, and each of that task finish its job with one record. And then the next step is exchange. And exchange, again, it's a data shuffling. It's moving data between the executors. So we see exchange happening, very small data being exchanged, of course. In this example, later on, we are going to have examples where there will be a lot of data moving. And then final count happening over here. And the results are being sent to the driver for the sake of displaying that for us. So that's the whole idea. We will be talking about that in detail shortly and explaining more things. Now, moving back to our notebook, let's run a second example where this time we are running a data for 2009 and full 2010, so 1 year more, and I will hit Control Enter to run it. And the idea will be the same. Spark will trigger a first job, just like previously, which will be very fast and one task. Then the job number 4, and this is where it's interesting. We don't have any more 12 tasks. This time in that job, we will have 24 tasks. So far, 0 completed, 8 running. And the idea is the same. Some tasks will finish earlier, some tasks will finish later. If some tasks will fail, then the total number of the tasks will be 25 or more. In our case, with so small number of data and so simple computation, I don't expect anything to fail. And here it comes. This job has been over, then was a third job, also very fast, one task. And this is a results display for us, meaning the data went through the driver for the sake of displaying that for the user. And if we go to the Spark UI to investigate job number 3, 4, and 5, and let's go to the tab jobs. So we see that the job number 4 does the job which looks most of the time 1.4, 1.6 minutes with 24 tasks. Let me click on the details and does a DAG visualization. It looks exactly the same because the task basically is the same, just volume of the data has changed slightly. And then by clicking on the stage number 5, it will take us to that nice visualization of the tasks. So right now we see that we have twice as many tasks, and now each executor has way more job to be done. And if we scroll down to the summary metrics for all those completed tasks, here the thing starts to becomes interesting because we see that the difference in size between the partitions, the smallest partition and the larger partition red, this is pretty significant. Here we have 300 megabytes and here we have over 500 megabytes, so the difference becomes really noticeable. And the summary of all the tasks. And for the sake of the exercise, let me go to the SQL and data frame tab to see how the things looks like over here. And the longest task, the longest jobs are over here. So I'm clicking on the description. And we can see that actually the execution route X is the same. So we are scanning CSV. Just this time, the volume of the data we're reading from the storage has almost doubled. And then we are doing the partial count on each slot, just like on our presentation. And the output rows is 24 because we have 24 tasks. Then we are doing the data shuffling, exchanging a bit more data being exchanged because a bit more tasks. Then we are doing the final count and we are returning results to the driver. So exactly the same idea. And as the last example in the notebook, just to show the contrast, let me read a single file from 2019 December. So that's significantly less data, but the structure of the application will be the same. First job very fast. Job number 7. Take a look on that. In this case, we have only one task. In this case, we were having only one task. In the first one, we were having 12, then 24, but now we have only one. So let's take a look on the details of the job number 7, stage number 9. And jobs number 7 took 8 seconds. And going into the details, we see stage number 9 looking exactly the same. Going to the stage number 9, 8 seconds, that's the data which has been read. If we scroll down, we see that there was only one task executed. It's because Apache Spark has decided that data is small enough. There is no point to split it across multiple partitions. He decided that it would be better to read it as the one partition, assign it to the task, and get a job done. What is reflected over here? Summary metrics of one completed task, 114 megabytes, and also over here, there is only one task. 114. What to split? If we scroll down, we see that there was only one task executed. It's because Apache Spark has decided that data is small enough. There is no point to split it across multiple partitions. He decided that it would be better to read it as the one partition, assign it to the task, and get a job done. What is reflected over here? Summary metrics of one completed task, 114 megabytes, and also over here, there is only one task. Okay, coming back to our notebook, that was the last example in this one. Key points to remember: driver plans a job and make sure that those jobs are being executed. If executor fails, it will take a task and assign it to another executor. And what is important, driver almost never touch the data. There are cases where it touch it, but generally it's avoid touching, doing anything with the data. Otherwise, it will become very quickly a bottleneck. And executor execute a task and report the status to the driver. There can be more than one executor on worker node, but in case of the databricks, as well as majority of the Spark implementations, it will be one-to-one, one executor on
Executor execute task and reports the status.
one worker node. There is as many slots on the executor as CPU cores. There can be as many tasks executed by executor in parallel as many slots. Task is the smallest unit of work. This is a frequent question on databricks exams. So for instance, if we have two workers, each 4 CPU cores, that gave us 8 tasks, which can be processed in parallel quarter on one worker node. Execute a task and report the status to the driver. There can be more than one executor on worker node, but in case of the Databricks, as well as majority of the Spark implementations, it will be one-to-one, one executor on one worker node. There is as many slots on the executor as CPU cores. There can be as many tasks executed by executor in parallel as many slots. Task is the smallest unit of work. This is a frequent question on Databricks exams. So for instance, if we have a two worker, but in case of the Databricks, as well as majority of the Spark implementations, it will be one-to-one, one executor on one worker node. There is as many slots on the executor as CPU cores. There can be as many tasks executed by executor in parallel as many slots. Task is the smallest unit of work. This is a frequent question on Databricks exams. So for instance, if we have two workers, each 4 CPU cores, that gave us 8 tasks, which can be processed in parallel on those executors. Data are being split into one partition for one task, and the driver and executor processes run on the Java virtual machine. By now, we were repeating a lot that the driver run on the Java virtual machine. By now, we were repeating a lot that the driver and executors sit on the separate virtual machines, which is not entirely true. There are other options. If we think about our own computer and then a data center or some virtual machines in the cloud, there can be actually 3 deployment modes. A local deployment mode is something that allows you to install whole Spark on your computer, driver and the executor, and this setup is mainly for playing around, testing, debugging. Maybe you want to develop something in such a setup. The second deployment mode is you can actually have a driver on your computer and executors in the cloud or in the data center, and this setup is good for developing something, testing, maybe interactive applications, but requires a good network connection between your computer and the data center. And the first setup, which is actually the only one which is suitable for the production workloads, is the cluster mode, which we're discussing so far, where a driver and executor sits in the data center in the cloud, and that's another frequent questions on the Databricks exams or Spark interviews. Let's talk about RDDs, data frames, and dataset. Since it is the cluster mode, which we're discussing, so let's talk about RDDs for interactive applications, but requires a good network connection between your computer and the data center. And the first setup, which is actually the only one which is suitable for the production workloads, is the cluster mode, which we're discussing so far, where a driver and executor sits in the data center in the cloud, and that's another frequent questions on the Databricks exams or Spark interviews. Let's talk about RDDs, data frames, and dataset. Some time ago, when you wanted to write another frequent questions on the Databricks, the first setup, which is actually the only one which is suitable for the production workloads, is the cluster mode, which we were discussing so far, where a driver and executor sits. Some time ago, when you wanted to write application which do something with the data, that data would be read into something what is called RDD, resilient distributed dataset. And resilient means that it's immutable, meaning once created, it cannot be changed. If we would like to do something with the data, then the new RDD would be created. And this strange behavior helps Apache Spark to achieve fault tolerance. And then our application would interact with the data, as we are going to see in a second, through the RDD API.